Hey, welcome to another Ian's Guides. Today we're going to be learning about how to find eigenvectors. So in a previous video, we found the meaning of eigenvalues and we found how to actually find eigenvalues. So now what we're going to do is we're going to shift our focus to eigenvectors. So using the same exact example that we had last time, we had a 2 by 2 matrix A, which was 5, 3, 0, 2. And from there, we found that our eigenvalues were 5 and 2. So now what we can do is we can start to find what our eigenvectors are. So we're going to have to use this format. So we're essentially going to use that A minus lambda times I format that we had before. So we'll essentially have 5 minus lambda, 3. We'll have 0, 2 minus lambda. And then we'll multiply this by some x and some y, right? We'll have some vector, and then we'll set this equal to 0, right? Because that's kind of following that format that we had before, where we said a minus lambda I times our eigenvector is going to be equal to 0 vector, right? So we're essentially carrying that over, and we're just using that here. So let's say we start out with our eigenvalue of 5, right? So we're going to have our A matrix of 5 minus 5, so we'll have 0, and we'll have 3, 0, and then 2 minus 5, or negative 3. And then we'll have our x and our y, and this will be equal to 0, 0. So now from here, we can see that these two rows are actually redundant, right? Because all we have to do to get this down to the row echelon form is we can really just add the two, right? We can essentially cancel out this bottom row. So let's only pay attention to this top row here. And from this top row, we will get that 3y is equal to 0. So now, what we can say is if we let x be equal to t, right, it's just some placeholder, then we can see that y is going to be equal to 0, right? Because 3 is non-zero, so y is going to have to be equal to 0 for 3y to be equal to 0. So then this leaves us with our xy as equal to t0, which we can actually factor out that t, and we can get t 1, 0, right? So this is actually going to be our first eigenvector. So we made it, or at least halfway there, We have one more eigenvector to find. So we'll essentially mark this, and then we'll come back to this later. So we'll mark that. Okay, so now for our second one. So we have lambda is equal to 2, right? So what we can do is in our matrix, we have 5 minus lambda. So we can do 5 minus 2, 3. And then we'll have 3, 0. And then we'll have 2 minus lambda, or 0. 2 minus 2. And then we'll have a different xy here than before. And then we'll still set that equal to 0, 0 to still mimic that form that we had. Now from here, we can see that we'll have 3x plus 3y, which is going to equal to 0. So then now we can say if we let y be equal to t, then we can see that 3x is going to be equal to negative 3t, or x is going to be equal to negative t. So then what we can say is that our xy here is going to be equal to negative t, t. So then we can pull out t, and then we'll get negative 1, 1. So essentially, we have our second eigenvector. So we're pretty much in the home stretch. Now, one thing I want to do real quick is I want to show us how to actually verify that the eigenvectors work, right? Because that's probably an important step to do at some point in the process. So now, remember, so we go back, so we have 1, 0, and we have negative 1, 1. Now, one thing to note real quick is with eigenvectors, they don't necessarily have to be unit vectors in order to be eigenvectors. So like, for example, right here, this is not a unit vector, our negative 1, 1. In order for this to be a unit vector, we'd have to do negative 1 divided by square root 2, 1 divided by square root 2. Because then, if we were to square that and do negative 1 square root 2 plus 1 over square root 2 squared, and then use the Pythagorean theorem, then here what we'll end up getting is square root of 1 over 2 plus 1 over 2, which will get us 1, right? Because then we know that's how we have our unit vector. So in this case, with eigenvectors, they do not have to be unit vectors in order to be eigenvectors. That's one thing that I wanted to note real quick. Okay, so back to verifying. So we can say for our 1, 0 eigenvector, if we have our matrix A, so we'll have 5, 3, 0, 2. And if we multiply by 1, 0, what we can see is we'll have 5 times 1 plus 3 times 0, and then we'll have 0 times 1 plus 2 times 0, which will leave us with 5, 0, which in this case, we can pull out the 5, and then look at that. We get the same vector as before. So this is essentially that first equation that we had, right? We had the A times V is equal to lambda times V. And this is exactly what we are looking for, right? Because we get the same exact vector that we put in here, our eigenvector. We get the same exact eigenvector coming out, except now we have this factor of lambda, right? Our eigenvalue. That's essentially multiplying onto this eigenvector. So now we can check the second one. And then with that, we associated that with lambda is equal to 2, right? So we said lambda is equal to 2 here. That's how we got that one. And then here we said lambda is equal to 5, which would make sense why we got the 5 out. So now if we were to do 5, 3, 0, 2 again, and then except this time we use negative 1, 1, well then essentially here we would get negative 5 plus 3, and then we would get 0 plus 2, or we would get negative 2, 2, which in this case we can pull out the 2, and then we get negative 1, 1 back. So then that's how we know that we have the right eigenvalue and eigenvector. So now you know how to use and how to find eigenvectors and eigenvalues. Okay, see you next time.